And today we're going to talk about chemical bonds. I know you're all excited about that. So let's get started here and see what we have in store today. In order to understand chemical bonds, you must know some things. So we want to make sure that we understand the two basic rules of physics: valence electrons, Lewis dot symbols, the octet rule, oxidation numbers, and electronegativity. And we need to have these things down in order to understand chemical bonds. Now, the other thing here is, before we get started, make sure you have a periodic table. If you don't have a periodic table in front of you right now, you're not prepared to succeed. Get your periodic table and get ready to learn about chemical bonds. The two basic rules of physics are this: opposites attract and likes repel, and nature moves in the direction of least resistance, which means nature moves towards the lowest energy. We have these two ideas down in order to work with the octet rule. Alright, valence electrons, the electrons in the highest energy level, and it's usually the S and P's. Electronegativity is the measure of an atom's ability to attract electrons to itself. And it increases as you go across, and it increases as you go up. Now remember, that doesn't include the noble gases. The noble gases right here, electronegativity is 0. They don't want to attract electrons. They don't want to give up electrons. They are good the way they are. They have their full octet or duet. What is chemical bonding? Chemical bonding is the process by which elements combine to form a compound. And a chemical bond is the electrostatic attractive forces between atoms strong enough for the atoms to act as a single unit. This attraction is created by the transferring or sharing of electrons. Now remember, in past lessons we've talked about electrons being the most important thing that we wanted to learn about the atomic model. And the reason we wanted to know about electrons is that it's electrons that determine the valence shells, and it's the electrons that determine the chemical bonding. And how elements come together and bond and form compounds is all dealing with the electron. We need to know about the electrons' ability to attract each other, and it's this transferring or sharing of electrons that's going to make the difference. And usually this involves the valence electrons.
The outer shell of many atoms, hydrogen being an exception, holds 8 electrons. Atoms that have an outer shell containing 8 electrons are considered chemically stable. We often say they fulfill what is called the octet rule. When atoms combine to form compounds, they can give up, accept, or share electrons in order to assemble an octet of electrons in their outer shells.
Two major chemical bonds. There's the ionic bond and the covalent bond. Those are the two major chemical bonds, and we need to learn about them. So the ionic bonds are created by the transferring of electrons. One atom gives up its electron to the other atom. Boom. And usually it's between a metal and a nonmetal, and they create ionic compounds.
An ionic bond forms when two atoms are held together by the attraction between opposite charges. The reaction between sodium and chlorine atoms is an example of how an ionic bond is formed. Since sodium has only one electron in its third shell, it has a tendency to give up that electron. Once it does, the remaining outer shell contains 8 electrons. This loss of an electron gives sodium a slightly positive charge. Chlorine, on the other hand, tends to gain an electron, since its outer shell already has 7. When chlorine gains an electron, it becomes slightly negative. The charged sodium and chlorine atoms are called ions. Ions of opposite charge attract each other and form ionic bonds. In this case, the attraction of sodium and chlorine form a molecule called sodium chloride, or table salt.
Example, there's sodium and chlorine, and you'll notice here that sodium wants to lose and chlorine wants to gain. That's perfect. So sodium is going to give up its electron, and so the electron is transferred to chlorine, and when that happens we create two ions. As soon as the sodium gave up its electron, it got a positive charge, And chlorine accepted that transfer, and chlorine got a negative charge. And what happens to opposite charges? They attract. And so now we have that strong ionic bond created by the attraction between sodium ion and the chlorine ion. Covalent bonds are created by the sharing of electrons. Now, it's not so much a transfer of electrons, but a sharing of the electrons between two atoms. It's between a nonmetal and a nonmetal, and of course they create covalent compounds.
Covalent bond is formed when atoms share electrons in order to satisfy the octet rule. For example, a carbon atom holds 4 electrons in its outer shell, but it would be much more stable with 8. To gain the additional 4 electrons, carbon can share with other atoms, and thereby have a completed outer shell. If 1 carbon and 4 hydrogen atoms come together and share their electrons, carbon achieves an octet of electrons. Note that each hydrogen in this compound achieves 2 electrons in its outer shell. This is the stable configuration of the first electron shell.
Here's an example. We have some hydrogen and some oxygen. Now notice oxygen wants 2 electrons. And so we had to have 2 hydrogens. But by sharing electrons, that gives hydrogen its duet, and it gives oxygen its octet. So everybody's happy. Okay, now let's look at some examples here. What bond will form? Sodium and iodine together. So what bond is that? Hopefully you said ionic. Hydrogen and oxygen coming together. We kind of already did this one, and it's covalent. Here's a lithium and fluorine. When they come together, ionic. How about carbon and neon? Neither. Why? Well, there's no bond because neon is a noble gas. The octet's full. It doesn't want a bond. It doesn't need electrons. It doesn't want to give up electrons. Then we have sulfur and fluorine, covalent. And arsenic and chlorine, covalent and somewhat ionic. Now it's a semi-metal and chlorine. Chlorine is very electronegative. And so I would say it's probably mostly or predominantly covalent. But you're going to see some ionic property in it because arsenic being a semi-metal and can act like a metal or a non-metal. So on that one, a little bit tougher, but still doable. And you can check that with electronegativities and determine whether or not you want to call it covalent or ionic. Note, ionic and covalent represent extremes. Most bonds are somewhere in between, where they're somewhat ionic and somewhat covalent. And what we look for is it mostly covalent or is it mostly ionic? And a lot of that can be determined by their electronegativities. You know, ionic is a metal and a nonmetal, and covalent is a nonmetal and a nonmetal. It's a good rule of thumb to help you determine the bonds that you're looking at. Let's look at compound characteristics. Ionic compounds are between a metal and a nonmetal, have high melting points, they have high boiling points, are crystalline solids. And as far as I know, they're all crystalline solids. The ionic bond is so strong that they're all crystalline solids, are good conductors of electricity, and most are soluble in water. Water, being very polar, attracts ionic compounds, and most ionic compounds dissolve in water. Covalent compounds are between a nonmetal and a nonmetal, have low melting points, have high boiling points, can be gas, liquid, or solid, depending on what's bonding and how strong that attraction is going to be, are poor conductors of electricity, and as a whole, most are not soluble in water. Even though some covalent compounds are soluble in water. Water is very polar. Remember, water is the universal solvent, and because water is polar, which we'll be talking about in a later lesson, it can dissolve more things than any other substance. But still, we consider most covalent compounds to be not soluble, especially your organic covalent compounds.